Welcome to Hess's Law. We're almost done with Chapter 10. Yay! I know a lot of you are pretty excited about that. Okay, Hess's Law. It's a way to describe enthalpy. And enthalpy basically means that it's a state function. And I'll talk more about exactly what a state function is. But the point is, with a state function, no matter the number of steps you take to get to the products, the total amount of enthalpy either used or released in the system doesn't matter. It's exactly the same as if you went in one step or you took 5 steps. For example, say I have reactants A here and I need to get to products over here. I can do this in one step, sure, A to D, no problem. And that, ladies and gentlemen, is going to require a certain amount of enthalpy, but maybe, just maybe, this reaction requires some ridiculously high temperatures or pressures or just something crazy that's not practical to do in most labs. But you can get around this by, say, going from reactant A to intermediate B. And if we do that, okay, so a certain amount of enthalpy is required. And then we could go from B over to C. Get another intermediate. Oh, let me spell out intermediate for you. Okay. We go from B to C and get another intermediate, and that requires another amount of enthalpy. And then I can go from C up to D. Boy, that's a wonderful straight line. Sorry. From C up to D and get to the product I needed, and I never had to do anything nuts like work with incredibly strange or high temperatures or pressures, or the other direction low is just as crazy, and I could still just do this in the lab. The interesting part about enthalpy is if I were to take the amount of enthalpy for delta H sub 1 and I added that to the amount of enthalpy for delta H sub 2, and I added that to the amount of enthalpy for delta H sub 3, these three together would equal delta H sub T for total. And it doesn't matter that I took 3 steps. Instead, I'm getting there simply straight from A to D. Another way to look at this is a strange sort of road system you could take, loop-de-doo, taking the scenery route. Well, even if you start at A and you loop through the scenery route, it's kind of like driving around the lakes around here, right? And you end up here, well, the goal was to get from start to finish. It doesn't matter the path that you took. Me personally, I kind of like take this, straightforward, get it done sort of route where you just, follow along the most efficient path. However, it doesn't matter. The end game, as you go from start to finish, is how we define Hess's Law. Well, how we use Hess's Law, but it's really how we define enthalpy. That is what is known as a state function. The path we take does not matter. That's what path independent means, these green words over here. Path independent means it doesn't matter the path you take. We're only interested in the start and finish difference. Doesn't matter how we get from one to the other. This is one of my favorite pictures to describe a state function. A state function, again, is what we call path independent. It does not matter the path you take. The change in enthalpy only cares about the start and the finish line. It does not matter. So, hey, if you want to stand, oops, I got that wrong. If you want to stand down here at the bottom, push the automobile all the way up here to the top, have at it. But notice the elevation gain is exactly the same as if you took this path straight up the elevator to the top. Elevation gain, in this case, would be a change in state from the bottom floor to the top floor. And the path that we take to get there does not matter. And enthalpy works exactly like that. It doesn't matter how we get there. Just get there some way. Using the idea of a state function, I'm now going to look back at sort of like what I did with the ABCD picture, but here we have path 1, A to B, and that's going to use a certain amount of enthalpy. But if I went from path A to intermediate C, it's going to use a certain amount of enthalpy. And even though this pathway looks like it's longer in terms of enthalpy, it doesn't matter, because I still am going to end up over here at B, at my products, regardless of whether I took path 1 or path 2. Now we are ready for the official definition of Hess's Law. Here we go. In going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. So, if we go from here, all the way down to here, the change in enthalpy is negative 890 kilojoules. Do you remember if that's exothermic or endothermic? Yep, it's exothermic. But what if, for whatever reason, I can't do this in one step and I have to go through an intermediate step? Well, the change in enthalpy from my initial position to the I guess that should be initial. From my initial position to the intermediate step is negative 670 kilojoules. And then the change from the intermediate step to the final step is negative 283 kilojoules, and the sum of these two numbers, sure enough, is going to equal negative 890 kilojoules. So I guess at this point you're just dying to know how we are going to use Hess's Law rules, and if you remember, I said something about these being puzzles. Well, there's just a couple of rules you need to know. Rule number 1, if a reaction is reversed, so if, I flip the reaction, the sign of delta H will also be reversed or flipped. So take a look at how this works. Take a look at this particular reaction. If we take these two products, well, that was silly. If we take these two reactants and make this product, it's an exothermic reaction resulting in negative 251 kilojoules. But if this reaction is reversed, flipped around, so now my products become reactants and my reactants become products, well, instead of the reaction being exothermic, where energy is released, you're going downhill, you have to go uphill. It's now an endothermic reaction, and the sign is also flipped. Now, if you remember, ages ago, I said enthalpy did depend on mass. It depended on how much stuff you have. So, if the coefficients in a balanced equation are multiplied by an integer, and that's really strange. I just noticed this. Integers, it could be multiplied even by a fraction. But you have to multiply delta H by that same integer or the same fraction, whatever it is that you decide to multiply each by. Well, I know you're dying to know why on earth would I need to do that. Trust me, that's coming. All will be made clear. Let's take that same reaction I used a moment ago where the change in enthalpy was negative 251 kilojoules. For reasons that I know are not yet clear, I'm going to multiply each one of those coefficients by 2. Well, what am I going to have to do to the amount of enthalpy? You guessed it. I'm going to have to multiply that by 2 because negative 251 kilojoules times 2 is going to be equal to negative 502 kilojoules. Okay, here it is. How to do Hess's Law and why we're doing this. Well, for starters, we're doing this because our end game goal here is to try to figure out the amount of enthalpy used by certain chemical reactions. So we are looking for the total amount of enthalpy for a reaction. In this particular problem, it states the following reaction, that's this one, was studied in a series of steps. These are the steps. Calculate the change in enthalpy for this reaction. So, Yeah, how are we going to do this? Well, I have some handy dandy tips and rules to help you. Number one, make sure that you write down what I call your goal equation. Write it down at the top of this problem. It'll make your life so much easier. So, yes, I highlighted it in blue. That is your goal equation. The second thing you want to do is find out of your series of reaction, that would be these, find the same first reactant as the goal equation. So I like to start with this one because they're puzzles. There's more than one way to do these, and there's no right or wrong way. However, I'm going to show you how I do it. It seems to work for me, and it's worked for many of my students. This is the very first reactant in my goal equation. And somewhere in these series, N2 as a gas, by the way, states of matter do matter. Anyway, N2 appears somewhere down here. And in this case, it appears right there. So what I would do on my paper, now that I've written down my goal equation, is I would write down out of the series of the two equations that were given, I would write that one down. Just that one all by itself on my paper because it'll help me get set up for step 3. Okay, now we're ready for step 3, which states identify the species in step 3 that you don't want in the goal equation. Well, let's see, I definitely wanted N2 because that's what I started with. I started with N2, so we want that one to stay right there. O2 needs to be there. I wouldn't worry about if it's where it belongs at this point because things will have a habit of changing as these problems get more difficult. But NO is not in this equation. Mind you, this is NO2 up here. It is not the same thing as NO. So NO doesn't appear in the goal equation. Groovy, you found it. Now, what are you going to do with that information? Okay, well, let's see. Let me remind you again. We found what we don't want. We don't want NO. And I said, what are we going to do with that? Well, we got to figure out how we can use that second equation to get that to cancel out. So there's a couple of quick rules that I didn't bother to mention earlier and you might kind of need. So we did some of this when we did redox reactions. So one of the first things you need to know is if they are on opposite sides of the arrow, opposite sides of the arrow, they subtract. And if they are on the same side, I got to write it way up here. If they're on the same side of the arrow, you have to add. And I'll show you how this works. In this particular case, NO is a product, and then the NO is a reactant. So because they are on the opposite sides of the arrow, we will get to subtract these out of a series of equations because just like we did in redox, we will be adding these equations together. Okay, last step. As I promised before, we are going to add these two together, much in the same way we did those dreaded redox reactions. Again, I'd like to remind you that we do have a goal. Our goal in this is to find out the total amount of enthalpy needed for this reaction. This was our goal reaction, and this is our series of steps. So we're going to add these two together. And let's see, N2. Does N2 appear anyplace else in these series of steps? Nope. So you can just bring that guy right on down. Yes, you should put the subscript indicating the state of matter down. In this case, I got news for you. States of matter, they do matter. Yeah, they matter. Yeah. So you should probably write them down. Anyway, moving on. N2. Okay, got rid of that. You can cross that guy out. 2NO, does that appear anyplace else? It does. It's over here on the product side. So 2 NOs minus 2 NOs, because they're on opposite sides of the arrow, cancel out. Go away. Add up to 0. You don't need them anymore. Now, look at this. We have 102 here and 102 there. They're on the same side of the arrows, so they add together. So we end up with 2O2. And yes, gas. And then lastly, and you can cross those out if you don't want to see them anymore. And then lastly, the last thing left is 2NO2 with a gas. And you add these two together. I guess I shouldn't have said last a minute ago because we still have to add these two numbers together. But when we do add those together, we find out that our change in enthalpy total is 68 kilojoules. That is the amount of enthalpy necessary for this reaction. In the next Hess's Law video, I will take you through some more example problems. For this first problem, the first thing I want you to do is not freak out about the fractions. The fractions will fall into place, so really, they're not that hard to work with, just don't freak out about them. Well, the first thing I like to do is get rid of the words, and then I like to write down my goal equation. This is the one I'm trying to find, so it's just good to have a good visual of what these things really are. All right, now I'm not going to use this one, but I do want to find sulfur somewhere in the white ones. Where do we find sulfur? Well, I find it in this first one. And the question I want to ask myself is, use it as is or flip it? And I'm going to use it as is because sulfur is a reactant, and I'm going to want it in the final equation right here as a reactant. So I'm going to go ahead and write that one down. S plus 3/2 O2 yields SO3. And keep track of these numbers. It's kind of like an inventory thing. So you want to make sure you keep track of your delta H's. Okay, that's done. Then the next question you want to ask yourself is, what don't you want? What is in the equation we just wrote down, this one, that does not belong in this final one? Well, the SO3 does not belong. So now we're going to look at the second equation and ask ourselves, the second white one, this one, and ask ourselves, how am I going to use this one to get rid of the SO3? And we're back to this question. Do we use it as is or do we flip it? Well, I'm going to want to flip it because I want it on the opposite side. Right now, under where I've drawn the blue line, it's a product, and over here it's a product, so they won't cancel out. So I'm going to go ahead and flip it. I like to keep the arrows in line, so that brings my 2SO3 over here, and now my reactants become products, 2SO2 plus O2. Now you got to flip this sign because I flipped the equation. So 198.2. Now I'm ready to try to add these together. But before I can add them together, you want to ask yourself, will the SO3s cancel? I've got 2 on the reactant side and 1 on the product side, so no, they don't cancel because 2 minus 1 is not 0. So I'm going to go ahead and multiply this top equation, this one, by 2. So 2 here, 3/2 times 2 is just 3. Multiply this times 2, which means I have to multiply this guy by 2. Now I'm ready to add it up. Do you see S anywhere else? Well, I don't either, so 2S plus. Do you see 2 SO3s? Yep, and since they're on opposite sides of the arrow, they cancel. Do you see oxygen anyplace else? Well, I see it here. On the reactant side, we have 3 oxygens, and on the product side, only 1, so that subtracts out to 2 oxygens. Now I want to make my arrow. I don't see SO2s anywhere else, so that's 2SO2. Now we're going to take out our calculator And we're going to take 2 times 395.2 and then add it to 198.2. And don't forget the negative sign. So that means we end up with negative 592.2 kilojoules. The only problem is this green equation does not look exactly like our goal equation. That's right, we need to divide each one of these coefficients by 2. That ends up with S plus O2 yields SO2, which means I have to divide this guy also by 2, which then gives us negative 296.1 kilojoules. And that's our final answer. I know how much you guys like fractions, so I thought not only would I hit you with another one with fractions, but this time we have 3 steps given to us in the series. There's a number of different ways to do this. I'm going to show you the way that always worked well for me. First off, please write down the goal equation. That will make your life so much easier. So there we have the goal equation right there. And I'm going to be looking for carbon dioxide. Carbon dioxide has to appear somewhere in this mess, so seeking out carbon dioxide, and I found him. He's right there. Okay, well, since carbon dioxide's a reactant, and over here it's a product, I'm going to flip this equation. So we start with 2 carbon dioxides, and that's a gas, plus 3 waters, and that one is also a gas, and that yields 7 halves O2. Don't freak out about the fractions, it's not that big of a deal, plus C2H6. And let's not forget to write down the enthalpy. Well, we had negative 283 there, so we need to make sure that we flip the sign because we flip the equation. Excellent. Often a good rule for this next step is if oxygen appears, ignore it until the end. Oxygen is almost always going to be like your worst nemesis in these problems, so do your best to ignore it, if at all possible. Okay, anything else in this equation I just wrote down that does not appear up here in the goal equation? Well, it's probably water. Oh, water's there. Oxygen. Well, oxygen's there. C2. Oh, wait a second. This one's not there. So let's see if we can find that somewhere up here. Oh yeah, and you can't use this equation anymore. Nope, used it once, can't use it again. So this time I'm going to use the very first equation, and that's this one. Do I need to leave it alone? No, you're right, I gotta flip it, because the one I'm trying to get rid of is a product there, and it's a product down here. That won't cancel. So yes, I need to flip it, and I do like to keep the arrows in line. So let's see, flipping it. C2. By the way, I keep saying C2H6. I gotta. That's great. I have an extra credit point if you look up the name of that one. Okay, now flip that one over. We have 2H2, and that's a gas. Should have written gas there. Plus, let's see, 1 C2H2. And because I flipped the sign on the very first one, I'm also going to need to flip the sign here. So 94.5. Am I ready to add these two together? Now you could do all 3 of these at the same time, but I like to actually just do them in sets of 2. It makes me, I know, less crazy, which will make things easier. Okay, well, the C2H6s, just as they are, cancel because we have a 1 here and a 1 here, and 1 minus 1 is 0. Now we're ready to add them. Do you see 2 CO2s or CO2s anywhere else? I don't either, so I'm going to write 2CO2 gas plus this one and this one canceled because 1 plus 1, well, actually 1 minus 1 is 0. What about water? Do I see that one anywhere else? Nope. So I can bring down the 3 waters, and that is a gas, yields, and hydrogen. Nope, I don't see hydrogen anywhere, so 2H2, and that's a gas, plus 7 halves oxygen, and I don't see that one anywhere, plus, bring that one down, and you're simply ready to add the 2 enthalpies now. So go ahead and grab your calculator and punch some numbers in. Okay, when you've picked up your calculator, plugged some numbers in, you should have come up with 377.5. And I am not going to deal with significant figures until the very end. Well, this equation is done for. I can't use this one again. And you want to ask yourself the exact same question. Is there something in this equation that does not belong up here in the goal equation? Well, let's see. I do need carbon dioxide. I do need water. Oh, I don't need H2. Well, how am I going to use this equation to get rid of the H2? Do I want to use it as written, or do I want to flip it? Yeah, I'm going to have to flip that one. I've had to flip all of these. Well, I'm going to have to flip it. Keeping the arrows in line. Let's see. So water now becomes a product. 1 water. And 2 hydrogens over here. Well, 1 hydrogen, just H2. And that is a gas. And water was a gas. Plus 1/2 O2. Well, I flipped that one, so yes, I'm going to have to flip that. So negative 71.2. Am I ready to add? No, not quite. For a couple of reasons. The first reason is the oxygens, well, like I said, ignore the oxygens. But the hydrogens have a problem. Here I have 2 hydrogens, and here I only have 1. So if you said multiply this equation by 2, you would be spot on. So if I multiply 1/2 times 2, well, I end up with 1. Multiply this times 2, I get 2 and 2. And yes, you have to multiply this by 2. And now we are ready to see what happens when we bring these down. Why don't you pause the video and see if you can do it on your own? I don't see carbon dioxides anyplace else, so I'm just going to go ahead and bring the 2 carbon dioxides down. And here I have 3 waters, and over here I have 2 waters. So those do subtract, 3 minus 2. And because I have more on the reactant side, I have 1 water that stays on the reactant side. Now I have 1 oxygen here, and I have 7 halves oxygen there. So 1 minus 7 halves, well, that's 5 halves oxygen. And since 5 halves oxygen, well, 7 halves is greater than 1, that's why it stayed on the product side. Now we have 2 hydrogens here and 2 hydrogens there, so those cancel. And then I'm left with this one, C2H2. Look at how nicely those oxygens worked out, and I didn't even have to stress about them. Does this equation in green match our goal equation up here? Yes, it does. Last step then is to finish calculating our enthalpy value. Now that you've calculated it, you should have come up with a final value of 235.1 kilojoules. Now I'm ready to deal with significant figures. Because this particular enthalpy value did not have decimal places, I do not want my final answer to have any decimal places. So my final answer for this is going to be 235 kilojoules. And we are done with this problem. Now I know at first glance this problem looks scary, and it isn't. Well, okay, maybe it is a little scary. I mean, I've been doing these 100 years, so I'm a little jaded. But this one just follows the exact same procedures we just went through with the previous problem, but now we just added one more step. And I want to caution you. Notice that here we have gaseous water, and here I have liquid water. Those do not cancel, subtract, or add. They're not the same species, so you cannot treat them as if they were the same species. They are two separate things. Okay, write down your goal equation and well, no, you don't have to write down the series of steps. That would just be a waste of time. I'm going to look for boron. Somewhere in this mess there should be, oh look, he's right there, right at the beginning. Okay, 2 borons plus 3/2 oxygen yields B2O3. And delta H then we have -1273, and I don't have to do anything to that number because I didn't do anything to the equation. Now, looking at this yellow equation, is there anything in here other than the oxygen that doesn't belong? You're right, the B2O3. So, since I can't use this one anymore, I have to find B2O3, and look, there it is, right there in the second step. Do I want to use the second one as is or flip it? Correct, you want to flip it. So we have B2O3 plus 3 waters, and this one has gaseous water, yields 3O2 plus B2H6. And because I flipped the equation, then I also need to flip that value. So 2035. Now, am I ready to add them? Yes, because both the B2O3s will subtract out of this problem. So I can add them up. I don't see any other borons anywhere, so I'm just going to bring that right on down. Plus, and let's see, there's B2O3 and there's B2O3, and there's ones in front, so they add up to 0, or like my students say, like to cancel out. I don't see oxygen, or sorry, I don't see waters anywhere, so I'm going to go ahead and bring down the 3 waters, and that is gaseous water. Okay, now I have 3.5 oxygens there, 3 oxygens there, and since this side 3 is greater than 3/2, you simply subtract those two and you end up with 3/2 oxygen plus the B2H6. So pick up your handy dandy calculator and find our current value of enthalpy. Okay, so I came up with, well, 762 kilojoules. And again, don't worry about significant figures until the very end. Looking at the blue equation, is there anything in this blue equation now that does not belong up here in the goal equation? Remember, ignore oxygens. Well, if you guessed water, gaseous water, you would be correct. And that means I need to use this equation. Do I want to write it as is, or do I want to flip it? You're right, I want to leave it as is. So I end up with H2O gas and H2O liquid. And because I left it alone, I can just bring the enthalpy value, use it as is. Am I ready to add these two equations together? You're right, I can't, because I have 3 gaseous waters here, but only 1, so they won't subtract. What am I going to do now? You're right, I need to multiply this equation by 3. Don't forget to multiply your enthalpy value by 3 also. Now I can add these guys together. Pause the video. See how you're doing with adding them together. I don't see boron anywhere, so I'm going to write 2 borons here, plus here I have 3 gaseous waters and 3 gaseous waters, so 3 minus 3 is 0. Those go away. I have 3 liquid waters, and I don't have that anywhere else, so I'm just going to bring that down. Arrow. I don't have oxygens anyplace else, so 3 halves oxygen, plus that's the only place I find diborane. And now I get to pick up my calculator and add them up again. And when I got one, okay, so adding them in the calculator, I ended up with 894 kilojoules. Finally, okay, that leaves this equation for the very end. What is up here in this goal equation that I don't want? See, somewhere in this green, I've got something that does not appear in the goal equation. I don't need water, and I don't need oxygen. But I'm only going to deal with the waters because oxygens tend to just kind of fall in line anyway. So do I want to use this last equation as is, or do I want to flip it? Well, if you guessed as is, you would be correct, because this one has water as a product, and I already have water as a reactant right there. So 1 water, and this is a liquid, so we're good to go on that. And over here we have 1/2 O2 and 1 hydrogen. And because I left the equation alone, I'm going to leave my value of negative 286 alone. Am I ready to add these two equations together? Nope. Because see, I have 3 waters here and I only have 1, so they won't cancel. They won't add to 0. So I want to multiply this equation by, 3. So we put a 3 here, and 1/2 times 3 is 3 halves, and a 3 here, and multiply this by 3. And now I am ready to add these 3 equations, the 2 green equations together. Let's see what I get. Do you see 2 borons anyplace else? Yeah, I don't either. So 2 boron, yes, that is a solid, plus, let's see, 3 hydrogens. Do you see 3 hydrogens anywhere? I don't either. So 3 hydrogens, and yes, that one is a gas. Do you see 3 liquid waters? I do too. They're right there. Those add to 0. They drop out. What about this 3 halves oxygen? Oh, look, 3 halves. Oh, they drop out. Told you the oxygens usually, fall into line, do what you need them to do. Just don't give yourself a headache over oxygens. And then, that brings the diborane down. Does the red equation agree with our goal equation? Almost. Got to write liquid. Now it does. Now you're ready for your final and last step, and that's to do the math. Okay, so once you've picked up your calculator and figured out the math, you should have come up with 36 kilojoules. And since none of the I'll try to say that again. Since none of the enthalpy values up here had a decimal place, I don't need a decimal place in my answer, and I am done. Now, I strongly recommend that both on this problem and the previous one, you go back and try to do those on your own, using the notes just as a guide, because not so much this one, but the previous problem, hint, is very much, wink, wink, nudge, nudge, like the type of problem I would put on an exam. Otherwise, have a great night. Up next, we have the study guide.